Dear classmates, welcome to the VLSI testing class. Today we are going to introduce the concept of Design for Testability, Part 1, Internal Scan Chains. We will introduce a very important scan architecture, the Muxed-D architecture. This slide shows a simple Muxed-D scan flip-flop. This is the most widely used flip-flop for standard cell design. This Muxed-D scan flip-flop has 3 inputs and 1 output, and of course 1 clock pin. The scan enable pin, or SE, select between 2 inputs. Data input is coming from logic, and the scan input is coming from the previous scan flip-flop. The data output pin Q and the scan output pin SO are often shared by the same pin. We can see that this Muxed-D scan flip-flop has 1 extra mux compared with a regular D flip-flop. So a Muxed-D scan flip-flop is 1 mux delay slower and larger than the regular non-scan flip-flop. This is the penalty that we have to pay for DFT. This slide shows the operation of a Muxed-D scan flip-flop. Suppose this is a rising edge trigger Muxed-D flip-flop. At the rising edge of the clock, if the scan enable is 0, data coming from DI is stored in the flip-flop. When scan enable is 1, at the rising edge of the clock, the data coming from scan input is stored in the flip-flop. So when scan enable is 0, this flip-flop is just like a regular D flip-flop. When scan enable is 1, this flip-flop enters a scan mode, which shifts the data from SI to SO. This slide shows a simple circuit with 3 flip-flops. Before DFT insertion, there were 3 non-scan D flip-flops. After scan insertion, those non-scan flip-flops were replaced by scan flip-flops. Also, we stitched them into a single scan chain. Output of Q is connected to the scan input of the next flip-flop. This circuit has 3 extra pins: scan enable, scan input, and also scan out. In normal operation mode, scan enable is always tied to 0. So this circuit is operating in the same way as the original circuit. The signal coming from the combinational logic is stored in the scan flip-flop. After 1 clock pulse, the data is then fed to the combinational logic. In the following slides, we are going to show you the test mode operation. We will discuss 3 different test mode operation. First of all, we will show you the stochastic fault testing. This is also called a basic scan by some commercial tool. In this test mode, we apply 1 test pattern for every scan chain shift. And then we will introduce delay fault testing, which requires 2 test patterns per scan. This slide shows the single SSF operation. The first and the second row shows how we apply the test pattern. The third row shows how we observe the output. The fourth row shows the clock waveform, and the last row shows the scan-enable waveform. In the first column, we load the scan chain by several clock pulses. At this time, scan-enable is held to constant 1. We apply primary input patterns as well as scan input patterns. Please note that primary input patterns remain the same for all the cycles. However, scan input patterns are different from cycle to cycle. After the test pattern is fully loaded to the scan chain, we perform a capture. At this time, we observe the primary output and then we pulse a clock to capture the response into the scan flip-flop. Please note that scan-enable remains constant 0 at this time. Finally, we want to unload the scan chain by pulsing several clocks. At this time, scan-enable remains constant 1. At the same time, we can also shift in our next pattern. And we observe the scan out of this pattern. This is a single SSF example. In this circuit, we have 4 squares which represent a scan flip-flop. The horizontal direction shows the data input and data output. The vertical direction represents the scan input and scan output. Suppose our target faults are SSF1 fault in red, SSF0 fault in pink, and the SSF1 fault in green. When we load the scan chain, we pulse 4 clocks. At this time, scan-enable is held at constant 1. We shift in 4 bits x011. Please note that the left bit is shifted in first. So this flip-flop would be x, this is 0, this is 1, and this is 1. At this time, we apply 1 to the primary input. After that, we can now detect this red SSF1 fault by observing the primary output. The good output should be 0, which is represented by letter L. If we observe a logic 1, then we detect the fault. So, how can we detect the SSF0 fault? We need to capture the circuit response from data input. So we pulse a system clock. At this time, scan-enable is held to logic 0. So for a good circuit, we will capture a logic 1 at this flip-flop. Also a logic 1 at this flip-flop. Eventually, we pulse 4 clocks to unload the scan chain. Again, scan-enable is held at constant 1. For the first scan output, we would expect a logic 1. If we observe a logic 0, then this pink stuck at 04 is detected. This is the same as the second bit. If we observe a logic 0, then the green stuck at 04 is detected. Now we will introduce the testing for two pattern tests. In two pattern tests, we will need to apply two patterns continuously. But this is difficult for sequential circuit with scan. So how can we do that? We have two solutions. Number one is called Longchamp shift. It's also referred to as skew load. Number two is Longchamp capture, which is also known as broadside load. This slide shows the Longchamp capture operation for two pattern tests. Initially, we load the first vector V1 by posing several clocks. At this time, scan enable is held constant 1. Followed by vector 1, we will apply vector 2 by another shift. At this time, scan enable is held at constant 1. And we apply a second pattern, PI2. We also apply 1 bit of SI2. After that, we would observe the primary output and pause a clock to capture the flip-flop. At this time, scan enable is held at 0. After the capture cycle, we will unload the scan outputs. At this time, scan enable is held at logic 1, and we pause several clocks to shift out the contents in the scan chain. And we can observe the scan output for this pattern. Please note that next pattern can be loaded at the same time. This is an example of LOC operation. For the same circuit with 4 flip-flops, we now consider one slow to fall port in red color and one slow to rise port in pink color. Suppose we pose 4 clocks to load vector 1. At this time, scan enable is tied to 1. So we now shift in X1, 0, 1 into our scan chain. And the primary input is don't care initially. For vector 2, we will pause another clock, hold SE to 1. We apply one more bit of scan input, which is 1. So the contents in the flip-flop will be changed to 1. This bit will be changed to 0. And this bit will become 1. This bit will be also 1. At this time, we apply primary input 1. So now we can observe the primary output. A good value should be logic 0, which is represented by letter L. If we observe a logic 1, then we detect the slow to fall fault. Now we are ready to capture the response into the scan flip-flop. So we lower the scan enable signal and post one more clock. And this way we can capture the response into this flip-flop. The good response should be logic 1. When we unload the scan chain, if the first bit is logic 0, then we detect this slow to rise fault. In this way, we can apply two pattern tests to the circuit. Long chunk shift is a very good scan application because it requires only combinational ATPG. No sequential ATPG is needed. However, it also has some problems. As you can see that the timing between vector 2 and the capture is very slow. This is because scan enable is a global signal, and the falling time of scan enable is limited by physical design. Typically, the fall time is around 5 nanoseconds. One solution is that we can route the scan enable as a clock, but it will cause area overhead. The other problem is that we could invoke transitions that can never happen in normal operation. The worst problem is that some transition delay fault can be untestable. This is known as the structural dependency problem. This slide shows the structural dependency problem. Consider this slow to rise fault. To detect this slow to rise fault, we will need a 0 to 1 transition. In the second vector, the side input must remain non-controlling value. However, because this 0 is shifted to this scan flip-flop, this is a conflict, so we cannot detect this slow to rise fault using long chunk shift operation. This fault is actually happening in normal operation, so we need to test the fault. But how can we do that? In the next following slides, we will introduce long chunk capture delay fault testing. In long chunk capture operation, we create the second vector by a speed system clock. Initially, we load the vector 1 by holding SE to 1, and we put several shift clocks. At this time, we apply primary input 1 and also shift input. When we apply vector 2, we create a falling transition. We control SE to 0. And we apply primary input 2. At this time, we post one clock, one system clock, to create vector number 2. Immediately after that, we can observe the primary output. and we also pose another system clock to capture the results, to capture the responses from the logic. After that, we unload the scan chain by holding SE to 1, and we observe the scan output. So we can see that the launch on capture operation creates a transition by the first clock and the capture the response by the second clock. So somebody also call this as double capture technique. This slide shows a LOC example. In this circuit, we have 6 scan flip-flops. Initially, we will need to load the test vector V1, 1, X, 0, 0, 0, 1. And initially, the primary input is don't care, X. To create the second vector, we control scan enable to 0 and we apply second vector PI2, which is 1. At this time, we would need to create a transition by posing a clock with scan enable equal to 0. So the first flip-flop would be 0, this flip-flop would be 0, and this will become 1, this will become 1. Now we create the falling transition to excite this low to 4 volt, and the side input is X to 1. So now we can detect the red slow to 4 volt by observing the primary output. The good output should be logic 0. If we observe a logic high, logic 1, then we detect the red slow to 4 volt. To detect this pink slow to rise volt, we will need to capture the response from the logic. Therefore, we pose another clock. At this time, scan enable is still 0. So we capture the response from the circuit. The good response should be logic 1. And this should be logic 1. Finally, we control scan enable to 1 and we unload the scan chain by posing 6 clocks. If we observe a 0 at the first output, we detect this pink slow to rise volt. So launch on capture has several advantages. First of all, as you can see, the timing between V2 and the capture is very short. So we can perform a true speed testing for the delay fault. Also, we can avoid the structural dependency problem of launch on capture. We don't need to change physical design. The scan enable signal can be routed as a regular signal. However, launch on capture suffers from long CPU time because sequential ATPG is needed. So we would need 2 time frames for the test generation. Now is the time for question. Are there any faults untestable by long-term capture? If so, should we test them, and how should we test them? Thank you for listening. See you next time in the class. Bye bye.